The next presentation is Upland Management and Precipitation Runoff Modeling System in Scott Valley. Multiple studies have demonstrated that targeted plant removals, controlled burns, and other activities occurring on the uplands of a watershed have the potential to profoundly impact downstream flow. However, the extent and nature of these effects are site-specific, and the specific implications for stream flow in Siskiyou County watershed remain largely unexplored. Of particular interest in the Scott River due to its important role as both a tributary of the Klamath River and a habitat for endangered salmon species. To better understand stream flow and upland recharge contributions in the valley, a precipitation runoff modeling system was constructed to estimate runoff and stream flow in the entire Scott Valley watershed. The PRMS model was designed to provide improved the Scott Valley Integrated Hydrologic Model, or SVIM, a mode flow-based groundwater model. SVIM is used by the local groundwater sustainability agency for the Scott Valley Groundwater Basin for groundwater sustainability plan implementation. The GSA and stakeholders are interested in upland management projects as a mechanism to sustainably manage the groundwater basin. Upland management scenarios for meadow restoration, juniper removal, and wildfire have been run using the Scott Valley PRMS model. To ensure model outputs match real watershed responses, statistical relationships between stream flow and precipitation were compared before and after a large wildfire in the South Fork watershed. Wildfires were chosen as a sufficient proxy for human-driven upland management due to their occurrence at single points in time, measurable vegetation impacts, and well-mapped extents. Both analyses demonstrate the impact of upland management on stream flow, ET, recharge, and groundwater baseware. Results will be used to enhance the monitoring network to better characterize impact and benefit of different management activities. Ladies and gentlemen, please join me in welcoming Dr. Foglia.
Okay, it was a long abstract, sorry. In the real life. I just want to give you a quick introduction of why we started working on this upland management. It was really not in the at the very beginning of developing the groundwater sustainability plan. It was not something that we were really considering. But then during the advisory committee meetings during the GSP, the plan development, we were doing it monthly. Now we are down to 4 times per year. And there was so much discussion about the upland. And it was happening in Scott, in Shasta, and Upland. So after hearing, you need to look into the upland, you need to look into the upland, we really started thinking about designing some new aspect. So that's it. Okay, the background is really that there is a lot of literature about upland, but what we are learning is that it's so valley dependent. So it's not that there is one rule that we can just apply everywhere. And you know, a lot of time looking about forest filling, prescribers, meadow restoration, juniper removal, the beaver dam analogs, other sources like fires, and really what we want to try to understand is how does this translate into what we're doing in Scotland. So our goal was really to evaluate whether upland management projects, and particularly we were looking into the western juniper removal because that was the one that was really mentioned pretty much every month for quite some time. And can those type of projects help improving water availability in the river? And there are 2 issues. So The first one is that the effects of removing a juniper are area and time specific. So that's why I'm saying there are papers that if you've done in other basins where they say, no, there isn't, it's not going to do anything to your general water budget, but actually there are other papers in other areas where you can see that there is an impact. And then the second issue is that other management projects that have taken place are occurring actually over a long period of time and are either relatively small, so they don't really make it a before and after. So sometimes you want to compare what happens before a project and after a project and have data that really can help you tell the story. And it was not easy to figure out location and areas where we could have let's say, a big juniper removal project with good data collection before and a good data collection after. That's part of the work. So what we did, we decided to use one of the big recent wildfire, and we used the wildfire as a proxy for upland management. So is that okay? Wildfire is cleaning up for the junipers or whatever, and that can be used as an example. So the advantages is that the fires that occur at a single point in time, there are measurable vegetation impacts, they are well mapped, and the only concern is there are concerns following the fire mirror to those following the target plan. So the concern following the fire mirror are very similar to the one that would follow a target plan. And so what we did is started looking into all the data. We got a lot of even paper material from the RCD and information, looking for a watershed where we could have a good amount of information from before the fire and for after the fire. So our goal was to really try to see if we could find a correlation between the stream flow and the fire. Because the general sense says, okay, after a fire, your stream flow will decrease. And but we need to demonstrate that and demonstrate that it works. And if it works, it's not bad. Okay. Wow, it doesn't say. Okay. So where did we find the best condition in terms of data? Was the South Fork in within the watershed. So the South Fork had a really big, large fire in 2021, and we have a stream gauge at the outlet of the watershed, which is that little highlighted piece down there. And the stream gauge was collecting data from before and after the fire. So we also use the French and Sugar Creek as a comparison. We call them controls watershed because they were not affected by the fire, but so also they were offering data. So we were basically comparing the watershed that has been impacted by the fire versus a couple of watersheds that were not. And the River Cocos fire, that is the one that affected the South Fork in 2021, was moderately severe according to the Forest Service categories. And approximately there was a 25 to 50% loss in canopy cover and living basalt area. So it was not extreme, it was a big fire anyway. And this is how it looks like. So the fire, the squares that tells you this is just the South Fork watershed, and the squares tell you the fire intensity throughout the area. So what we need to do once we start looking at the data that we have is we need to partition precipitation between rain and snow. So we need to figure out how to decide. So for the South Fork, we had a long period of effort through climate data, and we need just to find a way. Okay, what's the good temperature, and why do we need to do that? Is because of the amount of snow that was eventually falling just ahead of the fire was going to have an impact on how the fire is gone through the system. So we need to choose a temperature where all is snow and all is rain. And the story that which is the temperature. There is a little bit of uncertainty on which numbers to use. And it's I have to tell you that we really did a lot of trial, and the difference are quite significant if you take one or less degree. And so it's really like, you know, even in the weather forecast, we don't know if it's rain or snow. And it's really it is a very different picture at the end, depending on what we use. So we just decided to use many different scenarios, looking at the partition between all snow and rain. And no need to go into all the details, but I think in the end it was something like about 40 scenarios all together. And then so what we did is that each scenario was using temperature choices to separate its own temperature choices to separate rain and snow. Okay, so it's at the end we had 77 unique series of rain and snow for the southward watershed. So we have to put all this information together, and then we use these temperature decision and these temperature scenarios to really decide how to represent the snowman in our experiment. So basically, what we were, because you know, the question, the biggest problem is that it's not just the amount of snow that is piling up in the winter, but it's how this snowman is going to come into the valley later on. So that's the biggest component. So what we did is we ended up selecting some scenarios where we could see a very good correlation between the volume of the stream flow and the available liquid volume, and with liquid volume I mean rain plus. So in this plot, basically, if precipitation and flow were going to be perfectly correlated, they would be all on that black line. You see that I mean, they are clustered around, or it's a lot of statistics, but they're kind of telling us a story. And in the blue dots represent the liquid flows, and the orange dots are the summer flows. And then we went into different scenarios, and you can definitely see the difference between the blue and one. This one seems to be way more correlated. So we did this exercise for all the possible scenarios, and I think this was at the end the one that was selected as the most promising. So now let's look at the pre and post fire stream flow, and we look at the data from, I think it was about 2005 up to now, and basically what we have on the y-axis on both plots is the CFS, the discharge in the river. And then on the x-axis is just the time. And so if you see that the box plot that we have up on the upper graphic goes up, it means that there is more precipitation that is converted to stream flow. So in principle, in a fire situation, we would expect that jump that you see there between 2022 and 2023. It looks like the fire was 2021, and we noticed that it probably takes a little bit of time for the system to really show the differences. And one of the reasons might be that the very first year after the fire, there might be more infiltration that goes into the perforation and more runoff, and not necessarily just stream flow. So basically, the idea is that if you have a lower value for discharge, you have more precipitation that is used by other watershed processes. Okay, and so I think now what we need to look at is the time series on the bottom, and this is looking at the median flow response, and this one you see 2021, 2022, and 2023, and you can definitely see that 2023 the stream flow was so much higher. If you do the same in our control watershed, so we use the Sugar Creek, we still see that there is an increase, which also might be because we pick the watershed is one next to the other, but it's not as extreme as in the South Fork. And so basically, the idea at the end of the day is that we can use a control watershed and predict the response of the South Fork in case there was no fire. And basically, and this is what we did. So the gray area, the bottom area would be the stream flow in the South Fork in case there was no fire in 2021. So it has been just an exercise, but at the end it was it's really telling a story, and we can use it then for representing the same thing in the model. And okay, so the last thing that we looked at is looking at the observed versus the predicted response, and we were basically approximating the fire contribution to the stream. So in this plot is like from after the fire, and in red is the flows that is predicted with our tool from the fire, and the actual flow in the gauge. So there is quite a good correlation between the two. The main thing is that we can use the South Fork as a proxy for many other watersheds. Maybe we can try to understand a little better where to concentrate with our actions. And so these are the preliminary conclusions. Some severe wildfire can causes more stream flow to be produced from precipitation. So nobody would be really surprised by this. And this is likely due to the decrease in transpiration from the plants and more evaporation from canopy loss. And also there are other effects that are related to large-scale plant removal. And this is kind of just a graphic, that's what you would expect. So the implication is definitely that it looks like it's difficult to find locations where you really have data that you need to do all this type of study. But our goal would really be to use locations where we know something and see if we put this information into the model, what happens. So the next step was, skip this one, was really going into how do we bring all this information together into what we call the watershed model. So the watershed model really it has been developed for the entire Scott Valley watershed, and is looking into how much precipitation comes into the valley and how this precipitation gets distributed between infiltration, runoff, and stream flow. And I'm not going to talk about the first bullet. You heard so much about the groundwater model in Scott Valley. And but the idea here is that the groundwater model is fully integrated into this new rainfall runoff model. And this is again to just remind everybody, the purple area is the entire watershed for Scott Valley, and the smaller basin brownish in the middle is the active groundwater system. So the models runs continuously from 1990 to 2024. So we have quite a bit of data right now, and we are simulating the entire watershed in little cell size in 100 meters by 100 meters. We have quite a bit of resolution there. And we are using this rainfall runoff model to really simulate different scenarios already. So the model has been developed, calibrated, and then we started looking into upland management. Mostly what I will present today, some ideas for meadow restoration and the impact of meadow restoration to the water budget. And we have juniper removal and the wildfire. So the idea is that to see with the previous part of the presentation, I told you how we can use data to understand the impact of wildfire. And in this case, it's more nice modeling exercise. Okay, so I'll be quick on this, but through our collaboration with the Watershed Council, we got in touch with the USDA and the Forest Service, and we found out that they developed a model that is called the Lost Meadow model, that basically look into potential location throughout, mostly throughout the Sierra, but they did it also for Scott Valley. Location where there are meadows that were used to be there, they're not there anymore because of erosion, because of cattle, because of whatever type of impact. And the idea is to see, okay, what happens if we restore all those meadows? Is this going to yield more water into the groundwater basin? Is this a good, promising option? And the picture here, it kind of show you how it works when you have a good meadow and when you have something like not a good meadow location. So the meadow should be pretty shallow to be really acting like a meadow and storing more water. If it's very in size, like on the right side, then you don't have much of a storage. So we decided to couple our model with this lost meadow model that USDA developed. And again, because we were using the South Fork in the previous example, we are using South Fork again. So the map is just for the South Fork. USDA gave us maps that look into yellow meadows, that are the meadows that they think with high confidence they were used to be there, and orange are the one medium confidence. Everything, it's a model, so there might be errors, but basically the idea is that where there are, let's say, the yellow polygons, it's really where, based on topography, based on aerial imagery and whatever, they really expect that they really predict that, not predict actually, they're really saying that there was a meadow there in the past. And so the idea is to see what we can do. And so we put these meadows into our model, and we started looking at modifying some of the parameters so that we could see the impact of these meadows. And how did we modify the parameters? If there is a meadow, you expect bigger storage and a different type of vegetation parameters. So we went into our model, and I have to say, there was a lot of trial and error because we don't know exactly how to represent these meadows in the model. And we got some results. So we have more ET, evapotranspiration, that is lost during most of the year, which is kind of expected because you are restoring more vegetation. You have more groundwater storage, which is also very expected. We got smaller snow. That is not what we were expecting. So we probably need to go into the parameters and double check it again. We didn't have much time to do that. But then we definitely saw a greater stream flow, mostly in the winter. But we also didn't have, we also think that the smaller snowpack and a greater stream flow is our problem right now. Probably there is a temperature issue, and that's the reason why we see that. So what we want to do right now, and the plot here is just showing really the difference between the business as usual and the restored meadow scenario. So if there is a positive plot, is because the meadow, let's say, the restored meadow model is similarly some increase, and if it's like negative, it's a difference. So there are things that still we need to change and test, but it's pretty promising. At least it tells us that there is a way. We would need probably somebody that goes and find an exact location. Okay, here is a meadow that we can restore. Start looking a little bit more into vegetation, and have somebody that comes in and tells us how the vegetation may change there, so we can refine a bit the model. But it's definitely telling us a story. And then we did, the last thing I want to point out is we also mapped Juniper, and we got a lot of information from where are the biggest areas where kind of Juniper are really invading, and where there is more need to think about submitting. And for Scott Valley, it's really all on the eastern side of the valley, it looks like. And we did a quick run with the model again, imagining that in those purple areas that are on the east side of the valley that I showed earlier, we were removing all the Juniper. And again, these are model scenarios, so we were trying to do some extreme simulation. And what we could see is that we were having less evapotranspiration expected because we are removing the Juniper. So the Juniper are not there, they're not transpiring in the summer. And we definitely have more recharge, more groundwater storage, and more flow in general, and more stream flow in the system. So this is another very quick example, and I really want to say these are the first scenario that we run with this new model. So we are kind of learning, but at least it looks like you see the differences. So it means that there is probably something to think about. Yeah, so I think we have a tool now that it's more complete. So we coupled our groundwater model with this new watershed model that really looks into precipitation, and it's now just a question of asking questions to this tool and try different scenarios.
Comparing the fire versus no fire area, maybe I missed it, but we're comparing an increased runoff because of the lack of vegetation. Rain would run off quicker, it seemed. Did you take that into consideration?
So in that first example, we were using really the data measured at the gauge. And it exactly came out as there was more runoff into the stream flow. But it was not modeled so far. So we didn't run a model for the south coast, for the wildfire. For that specific case, we were just using gauge data.
All right.
Just
Yeah. All right, thank you so much. So we're going to take a short 15-minute break. And just a reminder, there will be another panel at the end of this session where you can ask questions that we get a chance to. All right, thank you so much.